Okay, everybody, we're going to get started. Um, Hope your day's been going well. Mine has been going unexpectedly. I've had technology trouble, computer that's down, so I've been chasing around town trying to get that resolved a little bit. So uh, when you have a kind of day that doesn't go quite as you planned, I mean, it throws everything off. But I'm happy to share some time with you this evening. I think it's going to be a valuable class. So my plan is at the start is to revisit some important logistical information with our test approaching. And then I'm going to spend time reviewing some content based on the first practice exam and give you a couple thoughts as we move towards your actual exam. So first of all, I've grabbed some information that's in the Carmen announcement section, and I just want to step through and draw your attention to some specific items. So first of all is obviously the date and time for the exam. Make sure you have that on your calendar. When it comes to administering it, the exams are going to be given in an unproctored environment, meaning there's not a added layer of security or something when you're taking the exam. So when you're thinking about resources or things that you could have available for that, I would definitely have a periodic table. I would have stuff that I would be able to write on. If you want, you could write on your periodic table, also have scratch paper, other resources like that. If it was me, I'd be planning to have those kind of things all set and good to go. It notes that when you're beginning to actually take the exam, you're required to agree to a honor statement to say that even though you might have, let's say, these other resources, you're still going to be doing the test individually. Now, what we found was when we did exams online last spring, there were hundreds of students that violated this code, because it turns out it's a lot easier to determine if people are taking the test honestly or not than you might think. All of the data when you take a test is being recorded. And it's really easy to look at internal data just to see if someone's taking it honestly or not. So I'm not saying that to spook you in any way. I'm just saying treat the honor code seriously, take the exam independently, and everything's going to be fine. We set it up in the fall, having learned from this, and we had very, very few occasions where it would be an issue. So I'm not calling people dishonest. I'm just saying that uh, it's just treat it honestly like you would any other test. Now, this idea here of the format, this is one thing that we learned that leads to uh, avoiding honor code violations, is that when you take the test, you're only going to see one question at a time, and you must answer that question in order to move on. And you can't return back to previous questions. So it's simply the case. Here's a question, try to answer it, move on. Here's a question, try to answer it, move on. That particular setup there, we need to do it because they're unproctored exams. So this format, though, it really hasn't, when we've looked at the data, it really hasn't changed students' performance within this. But I do think it is something that you might want to practice. And so that's why we have the practice exam set up in Carmen that way. I think a big benefit of the practice exams is it's going to get you comfortable with the particular format. And one of the aspects of the format is how it's being delivered. Now, as far as resources within that same section, it says prior to the exam, supplemental information that you might want to print out would include a periodic table and this other link to supplemental information. If it was me, I would absolutely print that out. I wouldn't want to have it as a file somewhere that I was seeking to access. So when it says this is information you'll likely need, if it was me, I would print it out and I'd be sure I have it instead of having it somewhere else electronically. Now, if you look at that, this is the periodic table that it leads you to, and this is the supplemental information. So you could print out the periodic table, you could draw whatever you want on it, you could supplement it, but I'd point out it's already a pretty good periodic table as far as showing the different metals, non-metals, metalloids, stuff like that. I want to draw your attention, though, to some points this evening of sort of some new ideas or other things that I want to add. And one of them I want to add is the to make you aware of the supplemental information for the exam. So on the exam, there's one grouping called constants and one called equations. This is the entire supplemental information right here. There's an equation that's used to describe the kinetic energy. That was the topic that we had within the first chapter. 1/2 mv squared, that's our equation for the kinetic energy. And paired with it, this constant here, this is a unit of energy called the joule. The units in that are kilogram, meter squared per second squared. So you notice within here, there's a mass and then a meters per second squared. So this is a set of units that you could use when you're discussing the kinetic energy. They both go together. So this is the only supplemental information that you have. If you have other supplemental stuff, you wanted to write it on your periodic table or something, you certainly could. Now, when you're taking the exam, very important here, there's a listing here, an entry that's talking about how to optimize your browser for it. When you click on that, it takes you to these details right here. Really important to make sure you've got your system so it's going to work properly. And the system so it's going to work properly, it gives you these very specific tips here to make it so your browser is going to be suitable. So all of these, when we had students set up within these, follow these suggestions last semester, there were no problems. Okay, it worked very, very well. So I think within this, it will work very well for you too. If you're able to update things, things are going to open properly, it's going to work fine. When you're actually taking the quiz here, the exam, here you see details within that. This is going to work for you. And when I say that, this worked for thousands of students last semester. If you're able to optimize your browser and then be able to go through the process, it's going to work for you. So you can be very confident in that. In terms of the scheduling, if you're seeking a time accommodation, there's some details for you here. It says that you should check the time limit on your exam the day before, just to make sure that it's showing up properly with if you're requesting extended time. And there's contact information there if it seems like it's not set up right. The reason why it says check in within here, in order to adjust the test time within the system, the staff has to do this for every single exam. They can't just click a button. They got to go through every single student. And I think they do a really good job with this difficult task of a lot of different accommodations. Just make sure it's done correctly for you as applicable. So if you've requested additional time, you can check that. And if you have any questions, this Gen Chem exams at osu.edu is going to be the source to check in on. There's also a description here about if you do have additional time, you want to make sure that you're starting it promptly so that you can finish it within that window. Now, that was something for the SODS. This last section here on the frequently asked questions, this applies for everybody. So please pay special attention to this one. So the first one, it says, can I use additional information like notes on my iPad when I'm taking it? And it says, yes, you can. There's not a lockdown browser, so you would be able to leave the app as needed and then return. That will work. My perspective is the technology is going to allow this. But is this a good test taking strategy? It wouldn't be for me. Okay, if I'm taking a time test, I don't want to have to get out of my exam and go track something down. Just with my own case, that would make me really nervous. Okay, that's like I'd be taking an exam in an auditorium and I get up and I walk down to the front and I'm trying to find something. I would not think that's a good strategy. So it's saying that technology would allow that. It's not locked down. But ask yourself, is that going to be a good test taking strategy? It's up for you to decide, but I'm just saying in my case, I wouldn't like to be going out of my test to try to find somehow additional information. I don't think it would help me.
Dr. Clark, can I ask a quick question?
Yeah, go ahead.
Back to what you were just talking about on the iPad. People are talking about it in the chat. I have like some of my notes on like Google Docs. So if I was going from like my Canvas tab to my Google Docs tab on my laptop, is that gonna like cause conflict in terms of honesty on the test?
It won't cause conflict. I don't think that that would be an issue in terms of the technology or in terms of the logistics within that. Uh, I come back to my own strategy though. I wouldn't keep it on a Google Doc. I would be taking it. I'm just thinking how now I'm not someone who's taken exams in this modern era like you have. I just know that if I took the information that I had in a Google Doc and I transformed it by writing it with pencil and paper and having that as a resource that I could access, it would serve me so much better on a test. So I guess I'm saying that the technology would work. You're not going to be locked down so you couldn't access something like that. Just ask yourself, is that going to be the best way for you to access that information? Okay.
Okay. Yeah. Thank you.
Yep. The a really good question, by the way. Thank you. The idea here, if you have a conflict within the scheduled exam, you might already know that. So you can go to see the makeup policy to request a makeup time. You'll notice within that the makeup time's actually after your exam, as far as when you can request it. What's going on there is every time we give an exam, there are students that just have last minute issues. Okay. Who knows? It's cars breaking down, it's different things going on. Life intervenes in all different kind of ways. So if something happens, even up to the last minute, and you are seeking to request a makeup, that's fine. If you know that you already have a conflict, I would say put in now. But I'm just pointing out that even if something happens quite late within that, it's not the end of the world for you. When you get started within here, one of the rules is once you begin the exam, you can't retake it. Okay, so once you've started the exam, you're going to be finishing it and working it within that window. What happens if your internet goes out or you've got some other connectivity issue or something goes on? Everyone, please note the contact information for that. Gen Chem exams at osu.edu. Everybody, please write down that information. Have that as a backup, okay? Put that in big bold letters in front of you some way, because if something happens, contact them during the exam and they'll try to be able to help you. So it gives that information right there. It says, do not wait until you have finished your exam to ask for help. Let them know. When you're taking exam, the staff right there, they have access to the exam. They're monitoring what's going on. They can come up with an answer for you. So everybody, please have that contact information. Everyone should write down Gen Chem exams at osu.edu. That is your crucial contact. I had the case that I had last semester. I had a student, they said they were taking the exam at home. They were all focused on it. The only person at home with them was their grandmother. As they were taking the exam, the grandmother decided to reset the router and broke the whole connectivity for them. So I don't know. Here's the person, they're throwing their grandmother under the bus by somehow saying that disrupted their internet. But I'll buy it, okay? Within there, this Gen Chem exams at osu.edu, that is your contact that you want to reach out to. They do say, however, a few things as far as, well, could you also make this kind of adjustment for me? This is about the only logistical thing that I saw within the program that people might have slipped up on, where this contrast between, are they ready to submit the whole exam or are they just moving on to the next question? Very small number of students had this as an issue, but they're just saying, please be careful with that. Now, what they're trying to do with these FAQ ones, these are things that we saw last semester. These are the main points. But if you've got any other question leading in, it's that same contact, Gen Chem exams at osu.edu. If you've got some other kind of frequently asked question, contact them. They are the people that are administering this and they do a really good job and they'll be able to help you in advance. Now, let me ask you this question. I want to shoot you a polling question, then I'm going to double back, okay? I'm curious within this in terms of as the exam approaches, if you think about both the logistics, how things have to come together, where you feel you are within your preparation, How do you feel right now? Do you feel confident, unconfident? Take about 10 more seconds. So allowing you to see where your classmates and you fall, I think I'd be about where you are at, where the majority of the class is as well. Somewhere between neutral and I'm moving towards confident, because I think that there's still going to be a lot of things that are still going to come together in the next few days. I think there'll be a lot of things that still come together in terms of your own understanding and your own practicing of the ideas. And I know that I went through some of the logistics right there. I tried to point out a few that were important, but for all of them, I really recommend, please look at those two set of announcements. Please look at those because those were set up by the people that know how the system works and they're trying to help thousands of students have it work for them the very first time, and it will, okay? So I think on the logistics side, we know what we're doing and that contact information will definitely help you. As time allows at the end of class, if you still have additional questions pertaining to the logistics, let's see if we can't take those up. But what I'd like to do now is pivot a little bit and move to some of the ideas that we had um, that I noticed within the first practice test. Some of them I'm going to add additional information to, and other ones I'm going to try to point out what I think are key ideas or mistakes that you might make. So uh, when you have your exam's going to be about 25 questions, plus or minus one. Okay, it's either going to be 24, 25, 26, something like that. What I've noticed within this is time can be an issue on the exam. When I see the amount of time that students take in practice exams, it's usually about, let's say, 55 minutes. On your real exam, when you have a 70-minute window, I find that the time of it, people come a lot closer to that particular deadline. And the reason why is I think when you're taking a practice test, if you don't really know a question, you say, well, I'll just choose A and move on. And on a real test, you're a little bit more deliberate, okay? You care a little bit more about it. You're a little more invested in it, and that slows you down a little bit. So the length of the exam, when I say time can be an issue, I'm going to try to point out a few things that might help you a little bit on time. It's not set up to be a 90-minute test, but I'm just saying you want to make it so you have your skill set put together so you can accomplish everything within the allotted time. It's going to be, again, about 25 questions. It's going to be drawn from chapters 1, 2, and 3. As you know, I've been trying to indicate the relative degree of difficulty that I'd expect for the different questions in each chapter. So what I'd like to do is step through chapter 1, then chapter 2, and then chapter 3, and share some ideas based on what I saw within the practice exams. And in general, I'm going to try to go from the easier questions to the more difficult. So here's ones that are from the first practice exam. So this would be a question that's going to be on the topic of identifying a chemical change or a physical change. I don't have a lot to add to this one. Students are going to do very well on this. This is going to be probably a 90% question. It's listed here in terms of a word description. I think you could also have it perhaps with a particle diagram of some kind, but identifying chemical change and physical changes, I think folks are going to do well on that. Another one that I think people will do well would be aspects of identifying how many significant figures are present and converting into and out of scientific notation. So this would be another one where if we're trying to go how many significant figures and into it and out of scientific notation, this is probably a 90% question. And when I say into or out of, this would be a question where you're sort of going in the other direction. express this particular value in scientific notation and use the correct number of significant figures, being able to write it something like that. So I think this is another a skill that you want to have, and I think you're going to be able to do well on this. This is one that's, I think, the next tier up. This is a little bit more challenging. So in this one, this is where we're now talking about measurements and we're applying terms like accuracy and precision. So in this one, it's shown in an image, but they're trying to show some sets of data. Two different students, student 1 and student 2, were measuring the mass of the object and they had different trials. And then you're being asked to say, well, can you compare the accuracy? Can you compare the precision? So both of those are technical terms for us. So take a second, I want you to pause. How would you evaluate accuracy? How would you evaluate precision? I think you need to know what those terms are before you can answer this question. So take a second, try to recall that information mentally. And when I say try to recall the information, you know, I do a lot with cognitive science. I read a lot with that. I don't know the best way to spend our time during a review. I think the best way is to have you give you prompts so you recall the information and see if we're thinking about it the same way. So when I say, how would you evaluate accuracy and precision? What comes to my mind is, okay, with accuracy, I need to know the true value. I need to know an accepted value that I can do a comparison to. For precision, with precision, I would be looking at the range of the different measurements. When something is in a narrower range, it's more precise. So when I'm looking at a comparison like this, it sure looks like student 1's values across the different trials are in a narrower range. I think student 1 has better precision. For each of those, if I were to try to compare accuracy, I don't know. I don't think I can compare the accuracy because I don't know what the accepted or true value was here. Another set of ideas within chapter 1 was when we were doing conversions involving the metric system. And sometimes we would set those up and we would be using dimensional analysis for that. The properties that we were looking at within this were things like temperature, but then conversions for sure involving volume, mass, and density. So when I see this question right here, it says a certain liquid has a density of 2.67 grams per cubic centimeter. What's the mass in kilograms if you have 30.5 mils? What's popping into my head as I'm looking at a question like this is, okay, I could use dimensional analysis to solve this. I see metric conversions that I'm going to need to know. Conversions between gram and kilogram. What's also popping into my head is, okay, the definition of 1 cubic centimeter is 1 milliliter, and that is an exact relationship. That's another thing that I think I'm going to need for a question like this. And then what's also popping into my head is, okay, anytime I have a question involving cubic units, I'm going to need to be careful. Because if I'm doing a conversion involving cubic units, I'm going to have to cube the entire term. These are what are popping into my head when I see this particular question. Now, if I look at it, I don't think I'm even going to have to do a conversion involving cubic units. I think I just need to know that 1 cubic centimeter is defined as exactly 1 milliliter. And I can then just do my conversion from there. An example where we would have to account for that, here's another one from the same practice test. Take a second, read this one for me. Couple things that I'm noticing within this one to draw it to your attention. So first of all, what I'm seeing within here is I'm seeing that when there are English units necessary, they're going to be given. This conversion between pounds and kilograms, okay, that's something that I'm going to need within the question because I got to somehow go from pounds to get into the metric system and end up in grams. But English units, those are going to be provided within a question. So that's one thing that you're not going to need to stress about. Another thing to point out here, this was inches squared, meters squared. we need to be careful with those square terms, just like we need to be careful with cubic terms, because that entire thing, both the numerator and the denominator, ends up being either squared or cubed as needed. Here's one other one that was from that first test. And when I'm bringing these up, when I say from the first test, these were all ones that were used on a previous exam, okay? This one right here, it says calculate the kinetic energy of an electron that's moving at a particular speed. I think this is a dimensional analysis problem, and this is one that ties back to the supplemental information. You don't have to have memorized the equation for the kinetic energy. You don't need to have memorized the units involving joules. Those were back in the provided supplemental information. All you need to do within this one is to say, okay, you have a mass in grams. If you want to get it into joules, you got to convert it into kilograms. And then you just plug it into the equation and you can get a value there in terms of joules. So,
Professor?
Yeah, go ahead.
I wanted to ask about this question because I did take the practice test, and when I was actually trying to figure this out, I got the answer 1.64 times 10 to the negative 14th, which isn't an answer provided. I checked my math twice, and it's the only answer I got. I ended up picking the one that you say is correct because I knew 1.64 was correct, but it was the best answer I could give at the time. So I was very confused that the right answer that I got is not an option.
Tell you what, let's keep going, and as time allows here, at the end, let's double back to this one, okay? Okay. This one, I want to draw your attention to what I think is the key error I would have within this one. So within this one, this is a mixed operation, significant figures. Mixed operation because I see that I'm doing addition and I'm also doing a division. So this would be my suggestion here of, I'm definitely going to stack up my addition terms. I'm going to stack them up and have them aligned based on the decimal point. And then when I do that, I'm going to see that I get a value of 14.06. I guess you could take down that last zero as well when you're adding them together, but you only have these 4 digits being significant. This is our rule of how we stack them up when we're doing addition or subtraction in order to determine how many significant figures we have. So that's why I see that I got 4 significant figures. That's going to be divided by something that has 4 significant figures. And that leads to what my answer is going to be on that. The idea of having a significant figures calculation that involves multiple operations, combining addition and subtraction, multiplication and division, I'm absolutely sure you're going to have a question like that on your test. To wrap up a couple topics within this one from chapter 1, this was one where we have a scenario and it says what is best described as a homogeneous mixture. Within this one, we were applying terminology like mixtures, whether it was homogeneous or heterogeneous. We were talking about things, whether they were pure substances or not, applying other vocabulary by looking at things and describing them, for example, as were they molecules, were they single elements, were they compounds? That was all vocabulary that we had. So as I look within this one, when I have a practice test, I'm sort of going to try to connect to some of those other ideas as well. I think air would be the best example of a homogeneous mixture because there's other substances. There's not a single substance. There's things like nitrogen there, there's hydrogen there, there's oxygen there, there's water vapor. There's a lot of other substances within the air. Carbon dioxide, I would say, is a pure substance. I would also say it's a molecule. And I would say it's a compound because it has different elements. It has carbon and oxygen there. I think liquid iodine, I would say that that's a pure substance. It is an I2 molecule. That's what I would be thinking about with liquid iodine. And with an apple, I think that's an inhomogeneous mixture. I think there's a lot of other things within the apple. It's not just, apple is not found on the periodic table. And it's inhomogeneous because there's like a skin region, there's a pulp region, there's seed regions, different things like that. So what I'm trying to do is to take this one and connect it to a few of those other ideas. This was another way of, yeah, go
sorry,
ahead.
I'm
Go ahead.
confused. How is carbon dioxide a pure substance?
What do you think it is?
No, it's just like I thought it would be similar to air. I mean, I knew air was the answer because I read the textbook, but I just don't understand why it'd be a pure substance. I know it can vary composition, but
yeah. So I would say when you say carbon dioxide, then
why wouldn't it be a
what?
pure compound? Yeah, someone just typed pure compound. Why wouldn't it be a pure? Like, what's the difference between a pure compound and a pure substance? Is there one?
There you can.
Because if you said pure compound, I would have gotten that.
Yeah, I think that a compound is actually telling you a little bit more. It's telling you a substance that is now comprised of different elements being present. So I think I think pure gold would be a pure substance. I think just carbon dioxide is a pure substance. I think sodium chloride is a pure substance. All of those, by having the formula, it doesn't vary from sample to sample. It's always just that entity. And with carbon dioxide, it's always just that entity. It's not like carbon dioxide somehow has a different formula or something. So if something always has the same specific formula all the time, and it doesn't vary from sample to sample, I would say that it's a pure substance.
Thank you.
Yep, you got it. This would be another one where we're looking at now a particle representation with those terms. When I'm looking within this one, if I have a particle representation one, I want to be sure of, well, what terms am I seeking to understand? So within this one, it's talking about a mixture and it's involving molecules. So when I'm thinking of molecule, I've got two or more atoms that are bonded together. And so within this one, well, it looks like I see molecules in 1, I see molecules in 2, I see molecules in 3. So those would all be examples of molecules. And with a mixture, what they're trying to do is to say, okay, the best example of that is when the molecules themselves are different from each other. So within that one, I think that's your best answer for what it's designating as a mixture. Within that mixture, I guess if I'm trying to use that vocabulary more, I see one type of molecule as a compound and another type is not a compound. That would be how I'm trying to use that vocabulary. One more idea within this one, and this is a new one that I sort of want to add to us. Within chapter 1, when we're looking at energy, there were two different descriptions of energy. There was kinetic energy and potential energy. And the potential energy that we're interested in as chemists is called the electrostatic potential energy. It has to do with the charges involved. So a new idea for us within this one. When we're thinking about energy, kinetic energy has to do with the motion of the particles. Potential energy has to do with their position. It has to do with their position and how they're being attracted or repulsed from each other due to the charges that you have. The things that affect that potential energy would be, when we're thinking about the position, it would be, well, how far apart are the charges and what is the size of the charges? This idea here of looking more closely at potential energy, we're going to do a lot of that within chapter 5. But let's add that as a new idea when we're beginning to think about describing energy in chapter 1. Kinetic energy has to do the motion. And we even have an equation for that, 1/2 mv squared. When we're looking at our potential energy, we're interested in how the particles are being attracted or repelled from each other based on their charges. And the force of that's going to depend on the distance of the charges that are apart from each other and also the magnitude of the charges. That sort of qualitative understanding, that's what they were asking on this particular test. Okay. Now, within this one, I'm curious within this. I gave an overview of the different questions that I saw within that first exam, and I tried to connect it to what I think the different learning objectives are that we've been working on. Now, you might feel really confident in chapter 1, work to do something like this. So I'd be curious, tell me in the chat, when it comes to chapter 1, what is your plan? Are there specific ideas you're still going to look at? Are you going to say, no, I'm good with chapter 1? Give me your own personal assessment here. What is your plan when it comes to ideas in chapter 1?
Am I able to ask a question about the pictures?
Sure.
It's random. Should we expect like black and white pictures, or will they be like colored pictures on the exam?
We used to only do black and white ones, and that's what that image was drawn from, because all the exams were then photocopied, and that's what we used, in an auditorium. Now everything is like a digital file, because that's how that's how the things are contributed. I think that they would be. I think that they might be colored, not simply black and white, but I don't think that that will be like the point of the question. I don't think it would say, oh, look at the red ones this way and the blue ones this way or something. I think that they would try to make it more, here's like something filled in and here's something open, to try to make it so that you don't really have to decipher that part of it. So they might be colored. I think they'll have better resolution than something that was photocopied, but I don't think the coloring would be the whole point of it.
All right, thank you.
Yep. Okay, so what I'm seeing within here, plan for chapter 1, the folks that are identified in particular, what does it mean to do metric conversions, dimensional analysis, involving properties like density? I absolutely think that's something with some practice you get better with. And you might have been better with that 2 weeks ago when you were practicing that more than you are recently. So if you're designating that as an area of improvement, I think that's a good one. And then I also know that the most difficult question from the chapter, lowest scoring, it's almost always significant figures involving a mixed operation. It doesn't need to be. It's the same plan all the time. Just make sure you have that plan and you're able to execute it. Now, when I look within chapter 2, we've got more boxes, more different types of questions, but it doesn't mean that this one has many, many more questions on the exam. In general, it's going to have about 8 questions, I would say, within chapter 2. Each of the chapters will have about 7 or 8 questions, would be my guess. And there's a whole group of ones here at the bottom involving aspects of naming and stuff that students usually do pretty well at. So let me show you some of those that showed up within the practice test. So I think this topic right here is probably the easiest in all of chapter 2. This is where we had the symbolism, where things could either be neutral, atoms or ions. And we had a superscript that told us the total mass. And from that, we are breaking it down to say how many electrons, protons, and neutrons are there. I think that's probably going to be the highest scoring question within chapter 2. And people were having good success with that on the pretest. When I was looking at aspects then of naming within that, a couple things that I want to point out to you. So this one right here, MGI2, what would be the name? So notice the format. It gives you the formula, and then it's asking for the naming of it. One suggestion for this, anytime I see one like this, before I look at the choices, I ask myself, well, can I name this without reading any of the choices? Because sometimes once you start reading chemistry names, they all sound pretty good. So I would say before I looked at any choices, I would try to name it myself. And this would be magnesium iodide, ionic compound. To add some ideas to this, when I see MgI2, I'm thinking that that's an ionic compound with magnesium 2+ and 2 iodide minus anions. It's not an I2 molecule present. I'm thinking how I could use a periodic table and see that magnesium is in my +2 column and iodine is in my -1 column. And in fact, we even know the names for the names for the columns. If I were to describe what was going on, I'm trying to extend this a little bit. I would say that the alkaline earth metal magnesium reacted with the halogen iodine, which is an O2 molecule, to form the ionic compound magnesium iodide. So what I'm trying to say is that within chapter 2, we did quite a bit with ionic compounds. We named them. We also saw that the charges our different metals would adopt when they became cations. And we saw the charges that our anions would adopt based on their column when we turned them into the corresponding anions. Information that you could add to your periodic table, you could add the charges that you typically see for those columns. Our +1 column for the alkalis, +2 for the alkaline earth. Aluminum's in a +3 column. If we go way over on the right-hand side, our noble gases are 0, halogens -1, then we have -2, then -3. If you're going to print out a periodic table and add some supplemental information to it, that's what I would add to it. I'd add designations like that. Here's another question. So this is also about the periodic table. So it says a biochemist is studying the properties of sulfur, and they're interested in whether some other non-metallic would have similar characteristics. So this is finding sulfur on the periodic table and thinking, well, what other element might be similar? And now notice the choices are. One of them is going further down the column, but it becomes a metalloid. One of them's going to the left, it becomes a metalloid. We've got an example that's right to the right of it and one that's right above it. And so we see in general, the properties are more similar when we're looking up and down the same column versus left to right. That's what we're trying to get at here. Here's another one from a naming one within chapter 2. This would be another example where I would try to name it before I read any of the choices. So the correct naming for this one is ones where we're using the prefixes, dinitrogen pentoxide. I'm looking at N2O5 and I'm thinking about this as being molecular. I have it being made, composed of nonmetals. I know that within this one, the most common mistake would be to name it somehow as an ionic compound. The idea of looking and trying to answer it before looking at the choices, I think that can make it so you don't talk yourself into something else. Here was one that was on the practice test. My comment on this one, so this was a polyatomic anion that you're being asked to name. I don't think you're going to have a question like this on your test. And when I say a question like this is a polyatomic ion that is other than the ones that I ask you to memorize. I think the only polyatomic ions that you're going to be asked to use are the ones that I ask you to memorize. I don't think you're going to have another question like this. This was one that we used on an earlier test, and I don't think it's as good a question because if we give it on an unproctored test, you can just Google it, okay? So I don't think it's a good question. I think saying that, oh, well, someone's going to know this, I don't think they would necessarily in the moment. So when I say I want you to know particular polyatomics, come back to this table right here. We want to know the name, the formula, and the charge for phosphate, sulfate, carbonate, these ones in bold. Nitrate, perchlorate, acetate. And I also see hydroxide as a polyatomic. These other ones I could use a periodic table for. So this would be a case of, if you know those, I think it's going to save you having to look up somehow information on the test like that. Now, as I'm thinking about this, these are all the anions. So take a second, see if you can recall this information. Is there also a polyatomic cation that I ask you to memorize? And would you be able to use a periodic table to determine these common charges? Use the periodic table? Well, I just mentioned a moment ago where we found our halogens as being -1, how we had a -2 column, a -3 column. So I think you could probably use that to come up, and that would be of assistance. When it comes to our cations, we had ammonia that became the ammonium cation. Ammonium is NH4 plus. Add that to one that it would be helpful to have memorized. This was a question that was on the practice test. This is really just trying to connect, was it a chemical or physical change? And tell me about the formula here. Was that best describing a molecular or an ionic solid? So this one right here, let me extend this one a little bit, because I know that when we asked this before on a test, it was close to 100% question. I think that this could be the same topic could appear differently though. So let me try to extend this one a little bit and have you think about it a different way. So let's say you had the exact same representation. And it was a chemical reaction. Which elements might it include? So within this one, I'm asking, which set of elements do you think could be arranged like you see as reactants? And then also being described here as the products? I think that's a pretty good question, okay? See if you can decide which set would be appropriate. Could carbon and nitrogen show up as reactants like this and then like products? How about sodium and nitrogen? Take a second, see if you can solve this, and then I'll share my thinking with you. Now, when I say, could it show up like this? If I'm looking at the products here, I see these diatomic molecules. I think nitrogen could be like that. I think oxygen could be like that. I think fluorine could be like that. So as far as these gases right here, I think it would work for nitrogen, oxygen, and fluorine. All of those I think would work. Now, if I look over here though, on the left-hand side, I think that that is an ionic compound. I'm seeing this extended arrangement of these alternating cations and anions that go throughout the three-dimensional object. And if I look closely, I think it's also being shown in a ratio of 1:1. We have the alternating pattern of white, black, white, black, white, black. It looks like it's an alternating pattern with a 1:1 ratio throughout. That's how I'm reading that image. So now I'm trying to look over here and say, okay, which of these could form an ionic compound with a 1:1 ratio, and then afterwards give me a diatomic molecule and the resulting solid? So if I'm looking at, I think the best choice would be if I was combining magnesium and oxygen, because magnesium's in my +2 column, oxygen's in my -2. So I think that would be in a 1:1 ratio for magnesium oxide. And then over here, these could be oxygen atoms, and this could be the magnesium solid.
If it wasn't a 1:1 ratio and it was like a 2:1 ratio, how would that picture be shown?
I think it would have to be, it's a little more difficult for me to describe that right here when they're trying to show it with a 3D arrangement. I think that a lot of times those would show up a little bit more where it would be stacked, and it would just be having two spheres of one kind and one sphere of another. I think that would be how it would try to designate that. I didn't have an easy example for that. I was looking at the one that was on the test and thinking, what other feature would be added to it? I think you have a good question on it. I think an ionic compound, many times it wouldn't be in a 1:1 ratio, but I think that would then be reflected into the ratio of the actual spheres that are there. When it came to chapter 2, we didn't have a lot of calculations. This was one of them that we had, where we were calculating atomic mass data. This was where we had information, in this case, that was provided where different abundance values were given and the atomic mass. If you recall, in order to set that up, it's the percentage of one times its mass plus the percentage of the other times its mass, and that's then what shows up on the periodic table. So this particular format, that matches how this question is being set up. But that same idea we looked at in different ways. We saw, for example, well, what if the information is given for what's on the periodic table and you're going to solve for the other terms? And this was one that we saw works when we had only two principal isotopes present because they add up to 100%. So we could call one X and one minus X. This is about the only set of calculations that we had in chapter 2. And that was the one where we were, again, using this expression, and we were either solving for what's on the periodic table or we were using what's on the periodic table, okay? Last set within here, and this is one where I want to add some new information for us. So this was one that was on a previous test. So it says these two molecules shown in the figure are, and it's asking about them. So let me add some more information for us. This was right at the end of chapter 2. Let me connect this to a few different things. So first of all, within chapter 2, we looked at different types of formulas: empirical, molecular, and structural. So take a second, see if you know what each of those describe. It's an empirical formula, a molecular formula, and a structural formula. The empirical, if you recall, that is when we have our simplest whole number ratios for the elements that are present as our subscripts. The molecular one is telling me the actual atoms that are present. That's what the subscripts tell me. And a structural one is showing me how they're actually arranged. So within this case, both of these have 4 carbons, 10 hydrogens, and an oxygen. So I think both of these descriptions right here, both of these molecules, they have the same empirical formula because this actually is reduced down to whole numbers. They have the same molecular formula, but they have different structural descriptions. The atoms are arranged differently. Now, a couple thoughts. We've seen that there's connections between the empirical formula and the kind of analysis that we do, like with combustion analysis. That gave us the empirical formula. It gave us something that we could use to determine the simplest whole number ratios. We added to that and learned about the molecular formula, but we needed additional information like the molecular weight. In order to get the structural information, I think we need even more information because we got to figure out how they're being arranged. Both of these would have the same molecular weight. Both of these are what then are called structural isomers. Isomers are things that have the same molecular formula, but the structure is different. The composition is the same. The atoms are the same that I have there, but the arrangement of them is different. When we're looking at ideas right at the end of chapter 2, talking about organic molecules, let's add this as one more idea for us. Let's consider how we can have different arrangements, and that shows up in the structural formula, and that those different arrangements are called different isomers. Now, within this group right here, when we're looking at this one, I'd say this example right here, that's an alcohol. It has this OH group on it. And in fact, this is something I think we could name. This would be butanol. I see a chain of 4 carbons and a hydroxide on it. This OH functional group, that turns it into an alcohol, I'd call that butanol. If we only have the chain of carbons, so it's just carbons and hydrogens, that was given the name of an alkane. The alcohol is a variation on an alkane where it has an oxygen present, and it turned it into a hydroxide group, this OH group. You won't need to know it, but just as an FYI here, this one on the left is something you might have heard of before. That's called an ether. In this case, it's when you have the oxygen, and on each side of it, you've got these carbon and hydrogen groups to it. You don't need to know that one. Let's just know the name, how we have alkanes, which are these chains of carbons and hydrogens. And if we substituted one of the hydrogens for the OH group, that turned it into an alcohol. I think that's a good level of understanding for us. Okay. Now, the last idea within chapter 2 is sort of the first idea in chapter 2. And those are the experiments of Thomson, Millikan, and Rutherford. Within this one, let me just give a quick overview within this one. For Thomson, Millikan, and Rutherford, those are the 3 scientists that we're interested in knowing about. And in each case, we want to know the scientist, the experiment that they did, what the significance was, and sort of how the experiment worked. I think this example question, I think this is in the how the experiment worked question. I think this was one of the higher end questions that you might encounter. Let me give a little quick overview here, see if this rings some bells. So the first person we talked about in that was J.J. Thomson. He was investigating cathode rays. He was taking a beam of cathode rays, which we now call electrons, and he was changing their trajectory by changing their path when they were affected by an electric field and when they were affected by a magnetic field. He found that he could balance those 2 forces and know the particular values and know something then about the strength of the electric field, the strength of the magnetic field. We had another force acting on that, which was the centripetal force. His analysis within that allowed him to determine the charge to mass ratio for the electron. He did the experiment with different cathode rays, and they all came and gave him the same charge to mass ratio. And he's credited with discovering the first subatomic particle, the electron. Within his analysis, then, he's determining a ratio involving the charge and the mass. He can't determine either one of those independently within that experiment, but he can determine their ratio. So he is credited with discovering the electron because he determined the charge to mass ratio for that particular subatomic particle. Next in line was Millikan. Millikan is involved with our oil drop experiment. We have this fine mist of oil drops that he has introduced into the chamber. They fall downward. He has an X-ray source that ionizes the air in the chamber and makes those oil drops acquire a negative charge. He doesn't know how much negative charge based on the X-ray, but he then turns on an electric field and he can suspend the drops within the field. By catching a particular drop and measuring the rate at which it rose and fell when he turns on and off the field, the electric field, he can determine the total amount of charge on that oil drop. And if you recall, within his analysis, then we sort of had our bar chart, which is like a histogram, and he saw that there was an increment that allowed him to go from one level to the next in terms of the amount of charge. And that smallest amount of charge, that increment, he said that was the charge of the electron. So J.J. Thomson had determined the charge to mass ratio. Now Millikan is able to actually calculate what the size of that charge is. With the size of that charge, now he could also calculate the mass. He could use both, get both of those. So he's the experimentalist that comes up with the charge of the electron. The last person that we had in there was Rutherford. So he was investigating alpha particles. Alpha particles were emitted from radioactive material. There were gamma rays that were emitted, alpha particles, beta particles. What were these alpha particles? So in order to investigate them, he did different things. One of his experiments was he directed it at this very thin gold foil. He expected that the particles would go through this very thin foil. And sure enough, almost all of them did go through the very thin gold foil. That was consistent with Thomson's plum pudding model, which said you just didn't have enough density of mass and positive charge to somehow deflect if you had this very energetic alpha particle going through it. So when Rutherford began the experiment and saw that a lot were going through, that was not revolutionary. What was noteworthy is when they did the measurement and saw that some of the alpha particles were scattered at a very extreme angle, and some of them even seemed to bounce back. How many? Very few. 1 in 10,000, 1 in 20,000. Very few were scattered like that. But that was enough to suggest, okay, this plum pudding model wasn't correct. And that led to a nuclear model where we see that within the atom, the positive charge in almost all the mass is concentrated in a very small region in the center. And most of the atom itself is empty space. That's my overview here of the scientist, the experiment, the significance, and how the experiments worked. So tell me within this one, here's our different sets. What's your plan for chapter 2? What do you think you need to focus on? Where are you going to spend time, do you think, in chapter 2? So I'm seeing a range of different responses within this. If you're someone that said you were focused on aspects of naming, polyatomic ions and the like, I would be using flashcards for that. I think those help within your recall. If you're someone who is focusing on, let's say, the mass spectrometer or the experiments of Thomson, Millikan, Rutherford, I think those are higher end questions. Higher end, well, they're at least lower scoring within that. When it comes to the idea of the experiments Thomson, Rutherford, and Millikan, at most, you're going to have one question on the exam with that. So I'm not saying it's not a good spot to spend some of your attention. I just saying don't overweight on that. You're not going to have 3 questions on that. For the questions here at the top, whether it's you might have one about one of the early scientists and maybe one about the operation of a mass spectrometer or the calculation of values, but you're not going to have 4 questions on that. Just to be aware of as you think about the strategic distribution here. Looking then within the last part within chapter 3, in some ways, these are ideas that you might be a little bit more familiar with. You may not have mastered them, but they're things that we've been talking about more recently in the class. Now, one idea or suggestion for you within this one, cognitive scientists talk about overlearning something. I think you've overlearned how to drive a car. When you first began to drive a car, you might have looked like this individual here. And so if you had an adult in the car, they would like stress you out because you were still learning all of the things that you need to do. Where to put the key in, how to turn, how to do this, how to do this. I think now you've overlearned it. I think you can drive for miles and miles, hours for hours, and you barely think about what you're doing. I think you've overlearned it and it's just now a habit for you. Now, what I'm trying to suggest is overlearning is something that comes with some repetition. I think chapter 3 really benefits from overlearning several skills. When you overlearn something, it means you quickly recognize the problem. You've got a plan that you know will always work, and you know how to efficiently execute that. When you overlearn something within this, it's not about being clever. Okay, you don't have to figure anything out. You just need to recognize it and apply the appropriate plan. When it comes to chapter 3, I think all of the more difficult problems here, the lower scoring ones, they're all things that you can overlearn. They're all things where you don't have to really be clever. You just have to recognize what the problem type is, know that your strategy works, and execute it. Let's see if that's true as we move through some of the ideas. So here's one at the start of chapter 3. So in this one, it's saying, so it's giving a word description. I think that this is in the topic of, okay, what you need to do is you need to know the definition for a combustion analysis, for a combustion. You're taking the ethanol, reacting with oxygen gas. It forms H2O and CO2. Then you need to balance it. And then the question is, okay, what's the maximum number of moles of product that can form when you have 1 mole of ethanol? Well, 2 of them gave me 10 in the balance equation, so 1 of them would give me 5. So this would be in the category here. It's a stoichiometry problem, but the real point of it is, do you know what a combustion reaction is, and can you balance it? Being able to go from a word description for a given reaction and balancing it, that's an objective at the start of chapter 3. This is one involving Avogadro's number. So there's a particular mass of the chromium nitrate, and you're asked to say how many nitrogen atoms are there. So a couple thoughts within this one. Notice how the question is giving you the atomic weight. It's not saying go look it up on a periodic table. This is a really common format that I'd expect on your test. Many, many times, instead of having you go look it up on the periodic table, the atomic weights are given. So that's something that you can expect. Avogadro's number, however, is not given. 6.02 times 10 to the 23rd is not given. So within this one, that would be a conversion that you'd have to be able to apply. So within this one, I would figure out, I'd use the molar mass, I'd figure out how many moles I have of chromium nitrate there. And then I would look and say, okay, how many nitrogens do I have for every chromium nitrate? And I would just scale it up from there. So I'd expect a calculation involving Avogadro's number. we had the topic of empirical formulas, and this was done a couple different ways. Within this one, you have percentages given for nitrogen and oxygen, and you're asked to come up with the empirical formula. You recall with this one, the strategy was we assumed that we had a 100-gram sample. We could use these amounts then to determine how many moles that we had of each, and then we would simplify that. Couple thoughts as I see within this one. When you have this data given, 25.9% nitrogen, 74% oxygen by mass, they are not talking about the diatomic molecules. They are talking about the actual atoms of nitrogen and atoms of oxygen. That's what shows up in these empirical formula descriptions. Second thing within here is, after you simplified that, this is what your value would be. And when I say simplify, it was divided by the smallest number and then looking to see what the ratios are. This is what you would end up with. Your work is not done then. We have to get it to the simplest whole number. So that would be the case where, oh, let me just double everything, and that takes it to the N2O5. So this is one example of an empirical formula question. Here's another empirical formula question. This I put in the category of, this is our longest question we might have. This one is a combustion analysis. My strategy for a combustion analysis one, I would use the amount of CO2 to get moles of carbon, the amount of H2O to get moles of hydrogen, recognizing there's a factor of 2 there, because there's 2 hydrogens for every 1 H2O. I could use that to get the gram amount of carbon and hydrogen as well. I want to get both of those because this one includes carbon, hydrogen, and oxygen. So I need to get the amount of oxygen by taking the difference between the original amount of sample and how much is now attributed to carbon and hydrogen. Now I've got all the details that I need in order to come up with the empirical formula. Moles, moles, and moles. And then finally, this one gives you information about the molecular weight. And we can go from the empirical formula to the molecular formula by scaling it up to make it so that it's now within that range. This is definitely in the category of have a plan. You want to be able to recognize something as a combustion analysis problem and have a plan. You don't want to say, well, I'm clever, let me start to now try to figure it out. Have a plan that you know always works for this. This one right here, I think, is something that you might not have a plan for. This is one that I think was intentionally an application that wasn't something that you could necessarily be practicing. So if you look at this one, you've got this Pb3O4. It decomposes to give you oxygen gas and this other oxide of lead. It's something like this, but this is not a stoichiometry problem. It's not something that you can balance because you're trying to figure out what those subscripts are. That was the goal of this particular question. If you know the mole amounts of each of those, you could come up with the empirical formula. So this one I know was trying to say, well, let's see if you can apply your understanding in sort of a new way. I think within this, you know how many moles of lead and oxygen you started out with because you know the mass of the sample and the formula. Some of the oxygen went to form O2. The other oxygen went to go into the product. So I think with that reasoning, you could figure out how many moles you had both in the lead, coming from the lead and the oxygen, and you could get the empirical formula from that. When I look at the early responses from this, I think people were doing quite well. A lot of people were coming up with PBO. And if you're in the category of, well, I'm really not sure how to solve this one, I think that this is not something to have memorized ahead of time. It's a little bit more of, can you figure out in the moment? So I don't think that this is necessarily something that I'd say you would have to overlearn. I think it's just how this showed up on this particular test. This one I want to draw your attention to the format. So within this one, this is a stoichiometry problem. It gives you a balanced chemical formula there, balanced chemical equation. It's telling you the masses. And then crucially, notice within the format, it's one where you're entering the value. It's not multiple choice. This one right here, I know on your test for some of the calculations, they're going to be ones where you enter the value, it's not multiple choice. Within that setup, I don't think they have to take any more time for you. Just do your best job with it. Just do your best job, enter the value that you get, and move on from there. This is one I want to make sure we take a moment with. This was the idea of looking at stoichiometry, seeing that we have some initial conditions, and then asking, well, what would we end up with? What would we end up with? And the two different variables that we need to have is we need to have the right formula for the molecules, and we need to account for if we have anything in excess. And within this one, almost the majority, we're choosing example 2, and that's perfectly done. So don't worry about our connectivity. When I'm looking for the molecule, though, I see Cl2O3. Those are going to be in the product. Cl2O3. That's what this grouping here is said to represent. And if we account for what's in excess, we needed to have this additional molecule here of O2 remaining. So the two variables that I want you to attend to with these pictorial ones is the right molecule present, and do I have excess that I need to account for? Here's another stoichiometry one. Now, one thing you would note right now, this is the third stoichiometry one I'm bringing up. On your exam, you're probably going to have 3, 4, maybe even 5 stoichiometry questions. They're all somewhat different. This one right here is one where it's asking about the percent yield. So it's giving you, again, format-wise, I see a balanced chemical equation, I see the atomic weights given, and it's asking about the percent yield. In this case, I have information about 2 different reactants there. So what's the plan? This would be my plan. I need to determine the theoretical yield before I do anything with the percent yield. When I determine the theoretical yield, I'm going to account for the limiting reactant. That will tell me, in theory, how much I think that I could produce. It also now tells me the actual amount that I produced. Let me turn that into a percentage. The actual amount you get divided by the theoretical times 100 turns it into a percent yield. So within these, first determine the theoretical, and then move on to your analysis to get the percentage. This is another stoichiometry one. So once again, if your takeaway is, man, there's several different examples of stoichiometry, I agree. They're testing somewhat different things. So this is, again, the key skill that I know is going to be overweighted on the test. Within this one, let's look at the format again. Within this one, once again, we have a balanced chemical reaction. We have atomic weights given. This one's asking the question, okay, what is the excess reactant and how much of it remains? So notice within the choices, there was a choice saying the H2O was excess. There were choices saying the other reactant was, and then we had the different amounts there. So I know within this one, multiple choice wise, this is really common how it's asked, because you've got options, well, which reactant was in excess, and you have different options for how much of it remains. Your strategy for doing this one, dimensional analysis would work. If it was me, I'm probably doing a BCA table. This last one is an example where I think a BCA table really helps. So within this one, we have a formula given, and this now begins its scenario. It's telling us the different amounts that are there. This was one where it was reported, not multiple choice, but tell me the value. So within the scenario, I would be setting this one up with a BCA table. These are the values for what are initially there. 5 moles of nitrogen, 10 moles of hydrogen, and none of the product. It tells me later on that I end up with 3 moles of the NH3. So it must have gone up by 3. Now I've got a value in the change line. As soon as I get a value in the change line, I can get the other ones by using the coefficients that I have that match up, because that's what the change line is telling me. And with that, then I can then see what do I end up with afterwards. So this is one that I think is very BCA specific. You can use BCA tables for any of the stoichiometry problems. At least with me, this is an example where I find it a really good tool how I can keep track of the different components that are there. So this was yet another stoichiometry problem. How many did we have on this test? It was like 5 of them or something. So it comes back to that, as I know, is a crucial skill that you're going to have to practice. This very last one, this was one that was on the test. this would be one that I put back into the category of something not to overlearn. This was one that was a scenario that was asking you to apply something. And when I say a scenario asking you to apply something, you're not going to have this identical question. You might not even have this identical skill. So in some ways, when I see questions like that on a practice test, sure, they're good to practice. They're good to give it a try. But don't stress, that's not going to be something that's going to be central and on your test itself. Now, tell me within this one, once again, what's your plan? What are you going to try to focus on within chapter 3? What is the specific feature that you think you want to spend some time with? As those are coming in, I really like a comment that I saw from Diana, who said that I'm going to be practicing stoichiometry, but I want to become quicker at it. All of the ideas are there, but I just need to bring the ideas together. Paraphrasing that, I think that that's absolutely an insightful comment. What it's saying is, I can recognize stoichiometry problems, but I sure would benefit by overlearning it with some practice. So as soon as it comes up, I've got a plan and I can just execute it and I don't have to try to figure anything out. I think that's absolutely the way to go. When I think back to my own undergraduate courses that I took, the science courses that I struggled with were ones when I could have overlearned something and I didn't. I could have overlearned something, but instead I thought, well, I think I'm smart. I think I can figure it out. That never helps on a test. If it's something that you can know and recognize and practice ahead of time, you definitely want to try to do that leading into an exam. And I think what I was seeing with a lot of comments here about empirical analysis and stoichiometry, they're absolutely in that category. Now, I've tried to illustrate a little bit how I think practice exams, the one that we had here, could be useful. Tell me about your plan for practice exams going forward. So I have a total of 3 of them available. I tried to break down this one as far as how it could be used and extended a little bit. My colleague, Dr. Stofus, has worked really hard putting together these practice exams with feedback. I think that they can be a great resource for you. Tell me what your perspective is, please. I think whether you've begun using them, you've done one and you're going to be moving on to the other ones, if you do them thoughtfully and you build on the feedback, I've seen the data. I know that it improves student performance. I can just see the scores go up from practice exam to practice exam and then lead into the actual exam. So I think the data tells me they are a really important resource if you use them thoughtfully. And as I look within the results, you're with me on that. So try to make that a useful resource for you. Now, as we wrap up within here, I just got 2 more things to share. There's been calls from my cat. So I want to share a little footage here. This is Rosie. I've got her on mute because, she can be loud sometimes. No great meaning beyond that. I just saw that we've had calls to see the cat. So that's Rosie. And then my last thought within here, as we wrap up tonight, I know that I really focus a lot in this class of, okay, I think this is information you need to do well on the test. I know that I focus a lot on different strategies and stuff, but at the end of the day, just do your best with it, people. I think I'm seeing so many good practices. Okay. Don't add any extra anxiety. All you can do is do your best with it. Okay. So even though I try to focus a lot on your success within that, because I know you care about doing well, you all are doing great as far as the different things that you are putting together. Okay, just do your best within the first test, and we've got plenty more exams in front of us. Let's just see how that one goes, and we can always improve our strategy as we need to from there. Okay, so try to stay real positive as we move forward. Send me questions if they show up the next couple of days. I got office hours on Monday. Let's do the best that we can to team up heading into that. And I'm really confident that we're on the right path. I'll hang around if you got questions.
I have a question.
Yeah.
So there was a question that you said it wasn't a stoichiometry problem. It's the
Yeah.
one, the 2.750 grams of PB3 question. That's the only one that I was like, I feel like I've never seen this before. I'm sure I have, but it was kind of just like an uh-oh, you know? Can you explain to me how you went through the problem?
Yeah. So within that one, I think that that's intentionally written so it's not something people have seen in practice before. I know it's
Okay.
one that set up saying, okay, well, can we figure this out? So within that one, if I double back to that, the reason I say it's not stoichiometry is you can't write a balanced equation for it because you don't know what this lead oxide is. That's what you're trying to figure out.
Right.
So if we say, well, what do we know? If you look within this one, I want to be able to get moles of lead and moles of oxygen in the product because then I can come up with the ratio. Well, if I look, I know how many moles of lead I started with because I know the mass and I know I've got 3 of them in the formula there. So, and I also know for the oxygen. So I could look at that ahead of time and figure out how many moles I have for both the lead and the oxygen. All of the lead then, those moles all go to the product. The oxygen, part of them go into the O2 and the other ones go into the product. So I'm using the information for how many moles I started with. Some of the oxygen doesn't make it to the product, but I know how much that is. That's what I'll use to come up with moles, and then I simplify that.
Is it bad that I'm still like a little bit confused?
No, I don't think you'll see this problem. I know you won't see this problem.
I was trying to look at it as, I mean, I didn't take the chapter 3 one yet, but I was trying to look at it as if I could do a BCA table, but I realized it wasn't coefficients, it was subscripts as you were showing us this, and then I just got more lost. But okay, I'll look at it the way that you're saying, so I'll go through it.
I think though that the 2 classic kind of empirical formula ones are, one is where you have the percentages given, and the second is combustion analysis. Before you worry about sort of a fringe question here, those would be like your core ones to make sure you're real confident with.
Got it. Okay, so empirical and percent. Got it.
Yeah.
Thank you so much.
You got it.
Also, I wanted to chime in. The last question on the Master in Chem from last night was kind of similar to this. And if you look it up, like it shows you steps of how to like do problems like that. And then that kind of helped me understand it more.
Yeah, I think that I won't say they're trying to disguise the one, but I think they're just trying to sort of broaden the type of scenario that might show up.
Would you say that the difficulty of the practice ones is similar to that of the actual one, or?
Before I answer, what did you think of the difficulty?
I've only done the chapter 1 so far, and I didn't think it was terrible. But I've heard from people that have taken it before that the actual ones are kind of worse than the practice.
No, I think that they're all. I don't think that the real exam is more difficult. I think that if you're a test taker though, you sort of perceive it differently because it counts in your head differently.
Yeah.
But when I see what the actual scores are, I don't see it like being necessarily an outlier. What I've seen before though, when it comes to multiple practice tests, I'll see a student and they'll get, let's just say a number. Okay, they get 60% on the first practice test. Then they take the second one and you can see they both, and then they moved up to like 68. Then they take the third one and then they're like 78. And so I see this progression as it goes up right from there. And so I think as long as you give yourself enough time leading into the actual test, you can make that progression and improve going forward. So before we used to have practice tests and they would be like, oh, here's the day before, give it a try. I think if you can start moving up that staircase where you still got 5 days or so here, I think that you can really see some substantial gains.
Okay, thank you.
Yep.
I have a question. Like I have two questions actually. Could you go back to like the chapter 2 where it's like the ionic solid decomposing?
Yeah.
I just have a quick like question on that one.
Okay.
This one. So how could it not be calcium and fluorine? Because I know those that makes an ionic solid, and then fluorine is like Hofbrinkel, so it would be F2 when it like as a molecule, as a
Yep.
molecular.
Good. Yeah, I'm with you. Now recognize within this one, I was just throwing together some ideas that would be paired with this one.
Yeah.
The reason I was thinking the calcium fluorine wouldn't work, I like the way that it could be here as far as the products. I could see those would be F2 and this could be calcium. But then I was thinking, I was trying to choose one where within the ionic compound, calcium fluoride would be CaF2 because calcium's 2+ and each fluorine's -1. And
Yeah.
that would give me a different ratio of spheres that I would initially have. That's what I was trying to get at.
I guess it's hard to see it in the ionic solid, I guess, because like maybe you could perceive, I don't know, it's 1-to-1 in the ionic solid, but it could be 1-to-2.
Yeah, I think that if the point of the question is, hey, can you see what the ratio is? It would be something that probably wasn't 3-dimensional. It would probably just be like the 2-dimensional one that we sort of saw in class before, and it would be a lot clearer to interpret.
Yeah, okay, that would make sense. And then also, there's one. It was about the mixture, you know what I'm talking about? In chapter 1.
Okay, let me go back.
And this is my last question.
Was it like a scenario one? Or was it,
This one.
yeah.
How could 1 and 3 not be a mixture of 2 different molecules? Because I see 2 different molecules in each of them. So
Well, and let's say look at 3 right here.
yeah.
Do you see that because you're saying, okay, this is darker than that?
Yeah.
Yeah, within this one, I know this was a photocopy one, and that's why they added this caveat.
Oh, is it not
Image quality is not the best.
Oh.
All dark spheres should be identical. I know this is one that they photocopied for the test, and they were.
Oh, so okay,
it
so
wasn't
those are all
helping.
the same then?
Yep, they're trying to say they're all the same.
They're not a mixture. Okay. Yeah. All right. That's
Yeah.
just why I was confused. That's it.
Okay.
All right. Thank you.
Yep.
I'm gonna be taking the test like delayed or a week later or whatever. Do you know if the questions will be drawn from the same bank? Or?
Oh, good question. I know they will be from the same bank. I don't know if that means you get any. I mean, it's sort of then random within that. I don't know if they intentionally try to exclude questions or if they intentionally try to have overlap. I know that the way the bank's set up, the exams that students get, they all are very equivalent. So it's not like, oh, the questions from the bank that you get would all be more difficult or easier to do. So I don't think it matters at all. I know that you'll get a random pull from it, but it won't be either an advantage or a disadvantage.
Okay, thank you.
I have a question.
Okay, I'm gonna go ahead and go.
Yeah.
I know that on mastering chemistry, an area that I was struggling with percent yield is if it's 100% yield, it will be one solution. But then the following question would be like, now imagine the percent yield was 75%. And that transition from 1% yield to now trying to figure it out with a 75% yield, I have no idea how to do.
Yeah, I know the question that I know exactly the one that you're talking about within that. In that particular one, I believe it was also like it had a particle picture. It didn't give you numbers. It actually had like pictures of molecules, I want to say. And so within that particular one, when it says 100% yield, initially, what it's really just saying is, well, what is the theoretical amount? Because with the theoretical amount, we assume we get 100%, right? Then within that next one where it said 75% yield, what that would be saying is, okay, so instead of getting all 100% of those, I have a smaller number. And that particular one, what it's trying to get at is something like this. I know the wording might be confusing, but what it's trying to get at is something like the very last one we covered here. Hang with me.
Okay, no
Like
problem.
that, something like this. So
Okay.
within this one, what it's trying to do is to say, okay, you don't get 100% coming over to be the product. You get a smaller value than that. So whatever that smaller value is, say that is what is in your after amount for the product, and then work the table backwards for that. So I want to say within that one right there, it was, if you treated it as 100%, you had like 8 molecules. If you treat it as 75%, you only have 6 there. So you would put, I would put it into a BCA table with 6 as my after value for product. And then I would just work it back to see what the other things would be.
So you will be looking at the product side and then working backwards?
Yeah, excellent. Yeah, I would be working on that because, yeah, good point. Because if you said, well, couldn't I begin to think about 75% for the reactants? I think that's going to mess you up. I would be looking at it because when it tells me percent yield, it's not telling me what the reactants has done. It's telling me about how much product I got. So use that for as a piece of information and then work backwards. And you can then deduce what happened to the reactants, but treat it based by thinking about the product.
Okay, and then you would obviously, not obviously, but you would take for this example, if the product is 3, it would be like 3 times 0.75.
Yeah, although this one I'm trying to think if this was, this is not the best example because this one's already has stopped you from getting all the way through, right? This, you know, so let's say you were supposed to get, let's say you're supposed to get 10. And it said, no, you didn't get 10. You only got 30% of that. Oh, so I didn't get 10. I only got 3. Now let me work it backwards from there. That's what I'm saying.
Okay, got you. Okay.
Yeah.
Thank you.
I think that it's a, I think it would be a clearer question if they told you the after amount instead of saying the yield there, because I understand why that's confusing.
Okay. Okay, thank you.
Yep.
I have 2 questions.
Okay.
So my first one is about the exam. Are the questions like weighted differently?
No, they're all weighted the same.
Okay.
And now, some are longer than others, but they're all weighted the same.
Okay. And my other question, I wanted to go back to chapter 1 very quickly. I just want to make sure I have this correctly for the significant figures problem that has multiple different operations.
Yes.
So, yeah, if you could go back to that really quick.
Yeah. As I go back, talk me through. What are you thinking?
So, I just want to make sure, like the way I've been doing it is that I do the operation in the parentheses first, and I keep the significant figures for that operation. And then once I do the second operation, I use, like, if the significant figures change, then I use that number of significant figures instead of the first one.
If you did your first step right here, would you have recognized that this gave you 4 significant figures when you did that addition?
Yes.
Okay. So yeah, I think that in some ways, that's the key step to have within this. I know that the most common mistake on this would be someone would say, oh, well, 0.820 only has 3, so I'm going to choose the one with 3, because that's going to be a lot quicker than if I have to do this other stacking it up thing. So if you have a strategy where you're already then stacking things up and you're seeing how that then affects the significant figures, I think you're doing it the right way.
Okay. because I just wanted to make sure, like, I know for the addition, it's the number that has the smallest amount of decimal places.
Yeah,
So with the 0.24, it has 4 significant figures, but it has only 2 decimal places compared to the 0.820.
yeah, I
Um,
agree. So
and
yeah,
then
so
for the
when we're doing that,
division,
that's based on the place relative to the decimal point. So I completely agree.
yes. And then so when we get to the division, say that instead of it being 2.910, it was actually 2.9. So
Mhm.
then the amount of significant figures would then change from 4 to 2, correct?
You got it. You got it.
Okay. So and then if it was vice versa
Mhm.
and it was still like 2.9, but I did the multiplication first and ended with addition, it would take it from, I guess, 2 to 4.
Yeah, I would say as far as what to do first and stuff, they're usually pretty clear of here's something in parentheses, here's another thing in parentheses. And so in some ways it doesn't matter. I mean, we have our order of operation that we use when we're going through them. And it's simply the case, it's not like the rules change. We just have to account for what's happening to the significant figures with each of the different sets of operations. So when I say that we can have the same plan that always works, I think you have the right plan. And I think if you go then through to see how each of the different stages, how they affect each other, I think it will always work out for you.
Okay. All right, great. Thank you.
Yep.
Oh, hello.
Hey there.
I just have one question on chapter 2, I believe.